Okay, this podcast is for CNT140. We're going to touch on Chapter 2. This was hopefully a big old review from CNT120, but we'll kind of buzz through it and maybe pull out some things that you might have forgotten about. Alright, so we're looking at popular LAN topologies, and the reason the book's talking about this is because the wiring of our building does affect kind of the topology of our network. That sort of idea. These kind of have to go hand in hand, my cabling and how things hook up. So they're mentioning this to get you thinking. When I specify a certain type of network, a certain topology goes along, I wire it a certain way, kind of thing. So, topology of LAN describes how each device will interact with each other. Yes, and there is a physical and logical, and I have a good example of that here in a couple slides. The physical and logical topology. The LAN topology is layer 1, absolutely. And the wiring layer, this layer 1 is critical. If anything here fails, my whole network's going to fail. Everything sits on top. So the three they mentioned for us is bus, star, and ring. So let's look at the bus topologies super quick. They mentioned this because our first Ethernet networks were bus topologies. They were coaxial cable connected together to form a bus topology. So if I look at the very first bus topology, 10-base-5 network, thick coax cable, what you had was a thick coax cable with transceivers that bolted around it, and a coax cable went from my PC, actually it was like a serial cable, went from my PC NIC into the transceiver. And then this coax bus acted as the central medium that all the computers communicated on. This went away after a handful of years and was replaced by 10-base-2, your thin coax bus. And the thin coax is actually thinner than what you have as a coaxial cable for your TV at home. It's thinner. Looks more like a twisted pair cable, about that diameter, that thickness. And here, what you had was on the back of your NIC, you had a BNC connector. The T connector twisted onto it, and then my coax connected into the T connector. Using, again, all these were BNC connections. A lot easier to connect for your network. And this was your first Ethernet networks, your coax buses. And if you remember, the data flow on this guy was, if a computer here wanted to send, once there was no data on the network, he would just send his data on into the network, and it would transmit to all nodes in the network. One giant, big old shared network. That's how it worked. And your access method for this was your CSMA CD, if you remember correctly. Collision detect. Hopefully I'm dusting off some cobwebs here from 120. Meanwhile, again, if you think back, Xerox was developing the bus topology for their networks, what we would call Ethernet today. IBM was developing a network for their computers, and they developed a ring topology for their token ring network. And initially, they used pseudo-twisted pair cabling to connect their nodes together to the MAU, multi-station access unit. Well, typically when they show a ring topology, they show a picture of something like this, and you're like, that's nice. But here's what's really going on. All your workstations are connecting into this MAU. Okay, all the workstations are connecting in using this pseudo-twisted pair cabling. Well, if you just look at this picture on the left, physically it looks like a star topology because all the nodes are connecting into this central multi-station access unit. And you'd be right, physically it looks like a star. But the way the token ring network worked with this multi-station access unit, it actually took an empty data frame and passed it out to a computer. This computer, if it had nothing to send, would pass it back out to the MAU, and then would pass it out to node B. And B would pass it back, and C would pass it back, and D would pass it back, and it would keep looping the network. So logically, you're getting this data flow of computer to computer to computer to computer to computer, looping around the network. That's where they come up with this logical, physical star topology and logical ring topology, because that's how the data flow is working. Well, if you remember also, if you did have something to send, you'd put your data into that frame, and it would loop the network almost like a little shuttle bus driving around. And where it needed to be dumped off, it would be dumped off or copied off, and then it would send back to the original sender, and the sender would say, oh, thanks, appreciate it, I'm glad it got there, okay, great. So if you remember your token ring, that's what this is going on. So again, your data flow looks like this, where it's literally just looping the network from computer to computer to computer to computer. That was your ring topology. IBM developed a ring topology for their token ring network to connect their computers together. Eventually, Ethernet adapted, got rid of the coax, replaced with twisted pair, initially like phone cabling, if you will, and they started connecting all the nodes into this central device and creating a star. That's why I have this little gray star in the background here. All the nodes connected into the central connectivity device. Initially, it was a hub, but eventually it became a switch like we use today. So our modern Ethernet network looks like this. Workstations are all connected into this central connectivity device. Oop, there we go. Or here's another example. All the devices connected to the central connectivity device. And if you remember, what advantage this gave us is it's definitely not less cable. It's actually using more cable than we had with the coax bus. But I do have the advantage of each cable coming in here individually. So if there's a fault with this cable here, it only affects that computer, not the whole network. Secondly, on my hub or switch here, I have blinky link lights over each port. So if I have a fault, I have a chance of seeing what the problem is. I didn't have that on the coax bus. Next, I have this idea of, or I should say I have this advantage of, if I want to plug a node in or unplug a node from the network, it does not affect anybody. Unlike the coax bus, if I'm plugging and unplugging those transceivers and BNCs and everything else, it affects the whole network. But with this star, as I plug and unplug this port, it doesn't affect anybody. Just think about it at home. I use this joke. At home, do you yell through the house, "Hey, I'm plugging in"? Or yell through the house, "Hey, I'm unplugging"? No, because it doesn't affect anybody. So I get some kind of admin benefits with this star topology and the twisted pair. I get some added admin benefits. So adapting the phone to data, over time we had to create standards and evolve the cabling to do that, but we went from the coax bus to the twisted pair star, so I could handle more bandwidth and those advantages we just got done talking about. And initially the standards kind of fell under the IEEE 802.3 umbrella Ethernet standards, and then along the way came your 568 on how do I cable all this so that it will work for this Ethernet network, if you will. Some standards were wrapped up in this to make all this work for our networks. So we get into 10100 based networking. We'll highlight these. We're going to come back in a later chapter and talk about different bandwidths and different standards for different bandwidths. So I'm not going to get too hung up on this just yet. We'll get some more details later. But initially, your 100 based networking, if you think back, as we went from the 10 base 2, 10 base 5 with the coax bus over to the 10 base T with the star, my device in the middle, my hub in the middle, repeats the signal to all nodes. Again, that had its own little problems, but as we move on to switches and so forth, which we'll talk about in a minute, that's going to help my network. Uplinks were used if I needed to connect more hubs in, if I needed to connect another hub to add more nodes. Again, that's going to affect my bandwidth, but I could do it. And I got rid of the whole transceivers and those sorts of things and started using twisted pair connections right into my hub or switch. And then each port on my hub or switch could handle 90-meter cable run from that hub or switch out to a workstation. This could be 90 meters if it needed to be. Okay. So the center of this now, originally hub, moved on to a switch using CSMACD, carrier sense multiple access with collision detect. Again, the hub would, whatever it received, it would repeat it out to everybody. But eventually the hub went away, and now we're using switches in the center of our network. The switches now, being layer 2, are going to learn MAC addresses and build a table. This MAC address is on this port, this MAC address is on this port, this MAC address is on this port. So when it receives a data frame, it will look it up and try to find where that MAC address is and send it out only that port. Hopefully you remember that from 120. And all that is helping to improve my bandwidth or my throughput in this network. As we said before, stations can be plugged or unplugged. It's not affecting anybody. I get blinky link lights for troubleshooting connectivity issues, and I can also connect in devices like OpenNMS using Simple Network Management Protocol to monitor my network and learn what's going on. Since I have a smarter node in the middle of the network, I can talk to the smarter node and let me know what's going on, almost like looking at the gauges on my dashboard of my car. And again, one station problem does not affect anybody else. These were all the advantages we just mentioned a little bit ago. 568 supports 10100 base wiring. Simple wiring of a hub or switch and nodes at the central point. Yes, absolutely. All the wiring is straight through. In other words, pin 1 to pin 1 on my outlet jack to my patch panel. White orange wire on this end on pin 1, white orange wire on the other end on pin 1. It's straight through the whole way through. And each leg is limited to 100 meters or 90 meters horizontal cable run and 10 meters of patch cables, like we said in Chapter 1, if you will. And here's I can use 568A or 568B wiring. We'll get to that details in, as we start terminating cable in the lab. We'll get to the details of that, but I can use either color code as long as I keep them consistent the whole way through. There is different standards for this. My 100 base TX is under the IEEE 802.3U standard. It's the simplest and most popular. You will see that on most things. 100 base TX. This is telling you that 2 pairs are required, one for transmit, one for receive. And again, I should be terminating all wires with 568A or 568B. That way I have those extra wires for things like Power Ethernet, powering an access point or IP phone, that sort of thing. But I'm limited to 90 meters, as we said before. The other standard, 100 base T4, you do not see this very often. This allowed for Category 3 using Category 3 cabling for 100 megabit. Most of this has been taken out and you don't see anymore, but this was a way to handle 100 megabit over Category 3 cabling. And again, 100 base TX has far outshadowed that. Here they talk a little bit about fiber wiring. I hate to say it's almost worthless, but it's almost worthless to talk about 10 base FL. It's 10 megabit baseband fiber. Okay, we're typically talking 10 gig fiber links today. So this is almost one of those. It's kind of nice to know. I've seen it, but the application for us is almost nil today. One of the later chapters, we are going to talk about gigabit and 10 gigabit copper and fiber standards. So we will dig in deeper on those chapters on these so we get a good handle on them. Last thing they mention is token ring, like we talked a little bit about. This was under the IEEE 802.5 standard. If you remember, 802.3 is Ethernet, 802.5 is token ring. Originally used shielded twisted pair and hermaphroditic connectors or IBM data connectors, and all those connected into the MAU like we showed you. Physical star, but logical ring for passing data like we showed you as well. And typically we're using STP. And if I were connecting shielded twisted pair cabling over to regular data cabling, the token ring cabling over to shielded twisted pair kind of thing. Here I actually needed a balloon transformer. That's what I'm trying to show you here real quick. The book mentioned a balloon transformer. Here's the IBM data connector over to twisted pair. I would need this balloon transformer to make that work. It's probably about the only time you see that, so I threw that in there for you. And that's really what they have to mention in Chapter 2.